Hi, welcome to the new chapter. The name of the chapter is Moving Charges and Magnetism. So, up to now we have discussed about static charges, static electricity, and charges which are moving, that is current electricity. Now, we are going to look at is there any way this current electricity has anything to do with magnetism? Is there any relationship of current electricity to magnetism? Okay. So, actually the electricity as such and the magnetism as such independently were known to us from more than 2000 years. Okay, so from 2000 years we have been knowing, actually we have know what is a they were able to find out what a magnet is, and there is a magnetic attraction, repulsion, electric attraction, repulsion, all these were actually known. However, only about 200 years back, the relationship of magnetism and electricity were actually seen. Okay, in the sense that the person whose name was Hans Christian Ørsted actually worked with, he was doing a demonstration in 1820. His name is Ørsted, Hans Christian Ørsted. In 1820, he was working with a demonstration of electricity, and he figured out that when the wire was carrying some current, by the side of it he took a small magnetic needle, compass needle, and it actually kind of deflected. So he figured out that there is a relationship between electricity, the flowing charges, and magnetism. So he then did a lot of experiments and trying to establish what the relationship was, and he figured out that it actually produces something called as a magnetic field around a current carrying conductor. And then the field itself, is like electric field, is not just a force per unit charge. Electric field is considered a force per unit charge, but at the same time we say electric field has its own entity. Okay, it takes some time for the field to change. So similarly, magnetic field also was thought of as its own entity. It exists and it can be calculated. So then later, later in sometime in 1800 or so, later than 1800, 1864 or so, Maxwell actually, James Maxwell worked on it and proved a relationship between electricity and magnetism mathematically, and he also came up with so-called electromagnetic waves. And he said that an electromagnetic wave is also not just these radio waves and all those things, but also the light is also an electromagnetic wave. So he was the one who came with that, and then later, somewhere at towards the end of the 18th century, we had actually towards the end of the 19th century, we had Marconi and J.C. Bose independently working and trying to show how you can actually use these electromagnetic waves to communicate. It's called radio communication. So this radio communication is one of the most important applications of what we talked about as a combination of electricity and magnetism. So the radio communication was as a technology was parallelly invented by J.C. Bose of India and Marconi. So this radio communication actually paved the way for all the communication today, to whatever you have in terms of TV and your mobile phone communication. Every one of them is based on electromagnetic waves, communication on the electromagnetic waves. So that is now the backbone, this particular thing of combining electricity and magnetism and called electromagnetic waves, is the backbone of today's all communications. So we will study about basically the relationship between electricity and magnetism. First we talk about how electricity produces magnetism in this chapter, and in the next chapter also we will get into the materials, magnetic materials, and how do they behave. And its next chapter will talk about actually how magnetism can produce electricity. So the opposite of it, like Faraday worked on it. So we will study these things. Now let's start with basically the first thing of how moving charges can produce magnetism, okay, magnetic forces. So let's talk about a I think we should start with basically electric charges. How do we work with electric charges? Let's say one charge is there here. You have a charge, and when you have a charge, let us say Q, some charge, capital Q, and that charge actually produces a certain electric field around it. And if you keep, for example, a point here, we define electric field as E as R. R is basically the vector here. E of R is the electric field at that point, which is a vector. Okay, so E of R into Q, which is, if you put a Q here, it will give you basically the force, small q. So this is what we have studied in the previous chapters. Then what we will see now is that whenever this charge, basically the electric charge, if it starts moving, so this E is actually kind of known to us, which is basically Q divided by 4 pi epsilon naught R square. So we know that. So suppose if you want to have a charge started moving, okay, this charge what we talk about has started moving, and when it starts moving, the charge Q here, so there is electric field. Okay, in the electric field here, the charge starts moving. Okay, what will happen? That is basically what we talk about as a moving charge. So moving charge actually experiences a force from the magnetic field, in the sense that this is electric field. There is an electric field here. Assume that I have a magnetic field. So magnetic field, I am going to write it as some magnet. Okay. So in this magnet, now this around this, assume that there is actually a magnetic field, which we call it as B of R at any point. So this from here, if you say this point, okay. So this vector I will call it as R. Okay. So magnetic field at this point I will call B of R. So if there is a magnetic, see, look at this, the two scenarios. First of all, there was an electric field here, and the electric field here was due to this capital Q charge. And now what we are considering is the electric field at this point. Okay, electric field at this point is E of R, and force on any positive, any charge kept here, small q, is nothing but Q into E into R, Q into E of R. Okay. So similarly here, okay, if you keep basically a charge here, okay, on at this point, let us say if you keep a charge small q plus q, okay, that charge, because of the magnetic field, does it experience any force? So what we are doing is, we have a magnetic field. Okay, I will call the magnetic field as B of R. Okay, that means it has a value of some with respect to every R, it has a different value, a vector basically. So now that B of R is there, and there is a plus Q charge I have kept here. But will it experience any force? That is the question. So the answer to that is that by practical methods, when you see that it doesn't actually experience any force. So whenever you are keeping a charge here at this point, it doesn't experience any force. On the other hand, if you actually make the charge move, okay, at certain velocity v, let us say the charge is moving with a velocity v, a vector, another vector. So let's say some velocity v is moving. Now when the charge is moving with a velocity v, then it experiences a force, which is called as a magnetic force. This force is F electric. So what force we are going to talk about now is magnetic force. That means a magnetic field. In the magnetic field, if you make one charge move, it will experience a force. So if it is moving with velocity v, what is the force that it experiences? Let us see. It experiences a force of v cross b into q. This is the force that it experiences. This is called as F magnetic. Okay. So what we are talking about is charge q experiences a force if it has a velocity v. So, if it does not have velocity v, if v is 0, then this is 0. Okay. And let us also see one more thing, this is v cross b. So, what is the meaning of a v cross b? We have to understand that. What is the meaning of a v cross b? It is called a vector cross product, in the sense that if you actually take two vectors and find a cross product between them. So, if these two vectors, let us say, are basically in two directions like this, one vector basically here, another vector here, two of them you can see the two vectors. Now, the resultant of this, not the addition, I mean there is a vector product or a cross product of these two, okay, will be perpendicular to both of them. Like the cross product will be basically in this direction. Okay, I will just take it as in this direction. Okay, this is perpendicular to both. So, either it is in this direction or down here, depending on whether you are crossing a, let us say this is B, this is A, are you doing A cross B or B cross A, depending on that. If you do A cross B, okay, then the resultant will be in this direction, and if you do B cross A, result will be in this direction, arrow like this. So, this is basically what we call a vector product. Vector product is always a product which we define it like this. We define the vector product as, if A cross B is defined as modulus of A into modulus of B into sin theta into n cap. So, let us understand this vector product. You must have studied it. I am just going to explain to you a little bit for this recap kind of a thing. So, vector product, whenever you do, you can see that if those two vectors, okay, so if there is an angle between them, okay, two vectors have an angle between them, these two vectors. So, this angle, let us say we call this angle between them as theta, between these two, okay. And if I keep it here, you can see this is the angle between them, theta. However, what we have to understand is this angle, if it happens to be 0, that means if they are aligned in the same direction, if the angle happens to be 0, then sin 0 is 0. So, vector product will be equal to 0, in the sense that whenever these two vectors, if they are aligned in either the same direction or opposite direction, that is parallel or anti-parallel, in both cases the vector product is 0. Okay, that is one important thing. And second is whenever theta is pi by 2, that is 90 degrees, when they are perfectly perpendicular, okay, then sin 90 is actually 1. So, if they are perfectly perpendicular, sin 90 is 1, and because of that you just get the multiplication of 2, A into B. Okay. And then n cap is just, this is all the full magnitude. This is the magnitude of the product. The product actually, the vector product, we call it as a vector product because when you are multiplying two vectors, you are going to get another vector as a product. It is called a vector product, or it is also called a cross product. We write a cross in between. Okay. There was another dot product which I viewed earlier. So, now this cross product gives you basically a vector, whereas the dot product gives you a scalar. So, the cross product gives you a vector which has a magnitude of A into B into sin theta, and its direction is given by the n cap. N cap is nothing but a perpendicular unit, a unit vector perpendicular to both A and B. Okay. Both A and B, it is perpendicular, and it forms a right-handed screw system between A, B and cap, n cap. That means whenever you have two of them, okay, let us say this is A and this is B. Now, when I do A cross B, I actually go from A to B like this. This is A and this is B. If I go from A to B like this, okay. Now, if I do that by keeping, let us say, a kind of a cap here, turn it like this, A to B, I turn it from your side when you are watching. A to B, when I turn it, what will happen? The cap will go inside. Okay, the cap will go inside means the direction is inside like this, down like this. Whereas if you do this to this, B to A, okay, then you turn it like this, the cap, and it comes outside, so it will be like this. So the way to do it is a right-handed system. It's called. I think you already know about it. I don't want to stress too much about that. So using the right-handed system, we can calculate the direction. The magnitude is given by this. So here also it is the same thing. V cross B, when you do, if both of them, if the motion is in the same direction as the B, okay, if the B is in this direction and motion also in the same direction, whichever direction B is, then there will be no force on it. The force will be there only if it is in the perpendicular, it has a component in the perpendicular direction. Okay. So this is basically what V cross B is all about. Now Q is basically what we are multiplying with that. This whole thing is called magnetic force. Now suppose if you are going to keep a charge, okay, if the charge is in both electric and magnetic field, if a charge is sitting there in both electric and magnetic field, it is moving actually, it is moving in electric and magnetic field, then it experiences two forces. So those are the two forces. Total force F, combined force is F electric plus F magnetic. If you add these two, you get Q into, okay, we can take it as common, E of R plus V cross B of R. So this statement, this force is called as actually Lorentz force. Lorentz, because Lorentz worked on it, this is called Lorentz force. So Lorentz force is about force on a moving charged particle. Okay, force on a particle which is moving in both electrical and magnetic fields can be calculated. By electric we already know, magnetic we now just now came to know if we add both of them. So that is what basically. So this again we are adding it vectorially. Remember that. So in this case actually if you see V cross B, when you do V cross B, okay, that V cross B is a perpendicular to both V and B. Hence it may be actually in a direction which is not in the same direction as E. Okay, if E and this were in the same direction, you could just add them. But since they are in a different direction, you have to actually add them vectorially. These two, when you add vectorially, you will get the final Lorentz force. Okay. So this is how actually a charge which is moving in a magnetic field and an electric field, that is the kind of force that it will experience. So remember this. This is, we are going to basically keep using this all the time. What is Lorentz force? V cross B. So now in this chapter we will actually concentrate more on the V cross B portion, okay, Q into V cross B portion of the Lorentz force, because we are going to deal with the magnetic part. Electric part we have already dealt with, only in some occasions we will use them. Most often when we talk about Lorentz force in this chapter, we actually mean the Q into V cross B force. Okay. So let's just look at various scenarios of how to use them. The first and foremost thing that we will talk about is a magnetic force on a current carrying conductor. So now we talked about one charge moving. Okay. If one charge is moving, this is what we found out what its value is. Suppose if the conductor carrying lots of charges, okay, they are moving, all the charges are moving, what is the force on such a conductor? Because that is more practical for us. We have a wire and current flows through that. What is the force that it experiences when I keep that wire in the magnetic field? So that is what we are going to find out now. So basically magnetic force on a current carrying conductor. So consider one conductor. Okay. Let's say this is the conductor. The conductor, solid conductor, and this conductor carries current. So what is the meaning of carrying current? We know that it carries a lot of charged particles and they are drifting. Okay, the drift, we talked about current, how the drift velocity of the charge carriers. So the charge carriers will be drifting. Okay, let the length of this be L and the area of cross section be A. So these two will take. Okay. Then we also take that let N be the number density of charge carriers. And Q is the charge on each carrier. So for all practical purposes, our charge carriers are actually electrons. Okay. So we'll just take it as charge carriers, and charge will be basically Q. That Q may be minus something if it is electron. Okay. So number density is number of charge carriers in one volume, one unit of volume. That is called number density. Okay. Now, what is the total number of charge carriers in this? That will be basically equal to N into L into A. L into A is volume. Okay. So volume, this is volume. So volume into number density will be is equal to total carriers, total charge carriers. Correct? And let us consider Vd is equal to drift velocity. Vd is equal to drift velocity. So we will also consider that there is a B. Okay, the B is the magnetic field. So it is all kept in a magnetic field. The whole thing is in the magnetic field. So the magnetic field now can be anywhere here in whichever direction. So what I want to do is magnetic field generally, see in the previous chapters we talked about basically most often we were able to do with 2 dimensions. Here we need 3 dimensions. So generally what we do is whenever 3 dimensions are used, we use when it is going inside and coming outside the board, we have some notations. Okay, so let's say if we write a circle and a dot or even a single dot itself, that is going inside the board. Like this, inside. So if I put basically a circle with a cross or just a cross itself coming outside, outwards from the plane. Okay. Suppose anywhere I want to write, let us say, a magnetic field which is actually perpendicular to the plane of the board and coming outside, I would simply put like this, dots, or I will put circles and dots. If I want to write a magnetic field which is perpendicular to the plane of the board and going inside, I would put like this, or I would simply put like this. So I put some crosses like this and say B. You have to understand that B actually is going inside, like this. Okay. So plane. So this is one of the notations that we are going to use. In this case, I am just saying that there is B. Okay. So now that B is either coming in or going out or any other direction, any other angle it is there, it doesn't matter. So generically I am taking B. Okay. So that B is some arbitrary direction is what I am taking here. Now with that, what we will do is the magnetic force that we have defined, magnetic force, is nothing but the total charge. Total charge is how much? Total charge is equal to Q into N into L into A. Hence force magnetic. So now onwards I will just write it as F, is equal to total charges Q into N into A into Vd cross P. So I am going to write it as Vd. Vd is nothing but our direction of the drift velocity, average drift velocity. For each one of them, if we take basically and vectorially add this, you will get Vd cross B. So this is the magnetic force on the current that is flowing through this. And this magnetic force, when we take, now we will define Q into N into let us say Vd, Q into N into Vd. We are going to define this as J, current density. Current density. So current density is nothing but this is number density into basically velocity into Q. That is our current density J. Now, so hence we can write this F as actually A into we'll say A into L into J cross B. A into L into J cross B. So what does that mean? This means basically now we are not talking about drift velocity, we are talking about already current density. Current density is basically current per unit area, that is the current density. Okay. So and it is a vector, it has many directions, current density into B. Now we are going to basically make sure that current density when you multiply with by A, will give you a current. Once you do current I, I will say these two together, I am going to only take the magnitude of that, and I am going to take the direction of J to the direction of L. L I will make it a vector. Now I will make it a, these two together. So I will write like this, L into A. So these two together I will call current I, but I will not make I a vector, I will make I a scalar. The direction I will get it to the L, which is nothing but the length, whatever we have, that I will make that as a vector. Why do we do that? Why do we not make I as a vector? That we will realize when we go a little further. So I am now take it as this much as a scalar I, and I will make L as a vector. It's very crucial actually, making L as a vector. So the F is nothing but, you can see, IL cross B. So IL cross B is nothing but the, say look at L. L is the length. Now I have taken the length as a length which is simply in one, without any curves, straight length. In such scenarios I can write like this, but that is not the case always. The wire may be like this, like this. If the wire is like that, then we have to take actually here this much area L is in this direction, in this area L is in this direction. See why we are taking L important here. So at every point if you take, L is in different direction. So we will take a small point, small thing as dl, and do a basically write it as, we will write it as I into sigma So sigma I into dl cross B over all L. This is actually the correct one. So for it's because the dl length may be same thing, but its angles are different. So when you do a cross with B, its values will keep coming differently. So you have to add them vectorially to be able to get the force on the conductor. So force on the conductor in a much more generic term is nothing but I into dl cross B over all the length L. And even you can actually do, when you get into even more continuous way, you do a integration of it. Okay. So this is nothing but the magnetic force on a current carrying conductor. Now we talked about this magnetic force. Okay, we talked about so called the magnetic field, which is B. Like electric field, we have a magnetic field here given as B. So what is the unit of magnetic field? So we'll try to figure out that now. Okay, what is the unit of magnetic field? So unit of magnetic field is so from this we can calculate actually if you see F magnetic is equal to Q into V cross B. You can figure this out from here, or we call it as basically QVB sine theta. Okay. So now B, if you take all the things as one, this is 1 Newton. Okay, let's say Q as 1 Coulomb, and sine theta will take, let us say, 90 degree or whatever. So this is nothing but V. Okay, we'll keep V unit as it is. V is nothing but what do we have unit for V? V is nothing but meter per second. Okay, meter per second. 1 meter per 1 second. Okay, that is B. So B is nothing but 1 Newton unit for 1 unit. One unit of B is 1 Newton into 1 second divided by 1 Coulomb into 1 meter. So something like Newton second by Coulomb meter. Newton second by Coulomb meter. That is basically our 1 unit of B, and it is called as Tesla. So in memory of Nikola Tesla, who worked a lot on magnetism and electricity. So 1 unit of B is 1 Tesla. But 1 Tesla is how much is 1 Tesla if you want to get an idea. Actually, if you see around, we generally use another smaller unit, okay, called as Gauss. This is also named after a scientist. So 1 Gauss is equal to 10 to the power of minus 4 Tesla. So this is a relationship. Just because Tesla is a big unit, we use a Gauss which is a smaller unit. Now if you want to find out the Tesla, if you look at the kind of things that we have, if you simply have a small bar magnet, generally will have 10 to the power of minus 2 Tesla. So that is kind of bar magnet, small bar magnet. That is a 1/100th of a Tesla. Okay, and if you look at basically Earth surface, because of the Earth magnetism, that would be around 10 to the power of minus 5 Tesla. That is 10 to the power of minus 5 Tesla. On the other hand, if you go a large field, we can generate a very large field in lab. That the maximum that you can generate around is 1 Tesla. and you can actually go and look at surface of a neutron star. Okay, surface of a neutron star, very highly magnetic neutron star, very powerful. Yeah. So that will be actually 10 to the power of 8 Tesla, very high magnetic, powerful magnet. But on the other side, if you go, okay, human nerve fiber, human nerve fiber actually has moving charges, and hence creates basically magnetism, and that would be of the order of 10 to the power of minus 10 Tesla. And if you look at interstellar space, interstellar space, where nothing actually seems to exist, also has amount of magnetic field, which is 10 to the power of minus 12 Tesla. That will give you an idea of the unit of magnetic field and how it is. So generally, whenever you talk about a bar magnet, it's 1/100th of a Tesla, okay, or about 100 Gauss. Okay. So like that, you can actually get a feel of the power of the magnet. So next, we will look at doing one or two small questions to get this idea of the force on the magnetic field. Okay, force on a conductor. Sorry. So let's look at the problem number question you take down. A straight wire of mass 200 grams and length 1.5 meters. Okay, it is mass 200 grams and length 1.5 meters. Okay, carries a current of 2 amps. Carries a current of 2 amps. It is suspended in mid-air by a uniform magnetic field B. It is suspended in the mid-air using a uniform magnetic field B. What is the magnitude of the magnetic field? How much is this magnetic field? Magnetic field magnitude, how much? That means assume that this is my wire. Okay. This is 1.5 meters and 200 grams, I think. Okay. So if you are basically leave it here, it will actually come down. Okay. But suppose if you have a magnet, okay, then what happens? Magnetic field is there. So magnetic field is there and current is flowing through this. So there are moving charges. Hence magnetic field will actually create a certain force on this conductor. So if the force on this conductor is in the upward direction, okay, then if that is exactly opposite to the force on this conductor by the gravitational force, then it will suspend itself in air. So it is possible to take a wire, conduct some current through that and make it stand in the air if you have a magnetic field. Okay. So now how should that be the magnet? Let's say this is the conductor. Okay. Let us say this is my conductor, okay, carrying a certain current in this direction. Now if the current is in this direction, now I want the force to be in this direction. F magnetic, I want it to be in this direction. So because we know that the F gravitation will be in this direction, and we also know this F magnetic is nothing but Q, nothing but I into L cross B. So this is L. Okay, what should be the direction of B so that F is in the upward direction? Okay, so let us say, I will talk basically as, let us say I have magnetic field here, which is going into the bolt. It's going into the bolt. So magnetic field is towards this direction, inside. Magnetic field is going inside like this. okay, and current is flowing like this. Now I want to do L cross B. L cross B means this is L, this is B, okay. L cross B, if I turn it like this, it will come up the bottle. So that means this is the direction of the magnetic field. So we have correctly written it, okay. So if we had dots here which is coming out, then L cross B would be like this and it would have come down. So that would not have helped it to suspend, because then the force of this and force of this would have been in the same direction, it would have fallen down. Now this actually is the correct way. So now we have to find out what is the value of this B so that it will stand, okay. Now how do you do that? Now you look at this, we know F magnet is equal to IL cross B, okay. For it to stand there, that must be equal to Fg. What is Fg? Force is nothing but mass into G, mg. That is the force going down. That is basically the weight. Okay. Now they have to be equated. So mg is equal to I into L into cross B. And since they are perpendicular, LB into sine theta, so that will be just L and B, ILB. Okay. So all the values we do have. So we have M, we have G, we have everything. We can calculate B. B is equal to mg by L into I. So M is 0.2, G is 9.8 divided by L is 1.5 into I is 2. So the value of B will turn out to be 0.65 Tesla. 0.65 Tesla. If we can produce a very high magnetic field of about 0.65 Tesla, you can make this conductor stand in the midair. Okay. That is basically what we have learned. So you can see that actually, in some sense, we may not really need the mass and L separately. M by L ratio, if somebody gives what is the mass density per unit length, that is sufficient. Okay, for any length you take, there would be no difference for that. Okay, suppose if you take the same wire of a different length, same B is equal to 0.65 Tesla will hold good. If you take double the length of this, then mass will also double, L also will double. So those two will cancel, you'll get the same thing. So it tells us basically that whatever may be the length of that, yeah, what is important for us is mass per unit length, and we also need to know what is the current. That's all is important to calculate the B. Okay. So this is one of the questions. So the next question let's take down is, if the magnetic field is parallel to the positive x-axis, positive y-axis, so second question, if the magnetic field is parallel to the positive y-axis and charged particle is moving along the positive x-axis, which way would be the Lorentz force would be, okay, for an electron and for a proton? So two cases. So in the sense that you have an x-axis here, okay, and let us say y-axis in this direction, and this direction is the, let us say, z-axis. Okay, so now what is basically given is y-axis left, let us say, is like this, going inside is the y-axis, x, y, z, like this. We can write like that. Okay, so which basically means that magnetic field is parallel to the positive y-axis. This is the positive y-axis. Magnetic field is parallel to that. That means magnetic field looks like this, going inside. This is my B. This is B, going inside. Okay, and charged particle is moving along the positive x-axis. This is the direction of the particle, V. Now V cross B we have to do. So look at this, V cross B, Q into V cross B is what we have to do. Okay. Now we, for A, in the case of electron, okay, so V cross B first we will do. V is like this, okay, this is V, okay, and internal going inside is B, going towards this side is B. V cross B means when you go from here to here, it goes up, okay. So the direction V of V cross B is like this. Direction of V cross B like this. We took the V, we took the B inside, and we did V cross B, which is the turning from like this, which means bottle cap going up, that is V cross B. V cross B into Q, Q is negative. So when you do minus of that, it will become like this. So if it is electron, okay, electron actually starts moving like this. The force will be like this on the electron. So electron is the charge is moving like this, and on that, to perpendicular to this, this is the direction in which force F magnetic applies. Okay, so that makes this one actually start bending like this if it is electron. On the other hand, the B, okay, so we can say for electron it is negative z axis. For proton, we just go positive Q into V cross B. V cross B when you did, it went up, so it is up like this, which is positive z axis. Positive z axis means like this. So that means this actually makes a turn like this. So you look at this now, always whenever you talk about a magnetic force which is actually applied on a charge, it never actually either it never increases the speed of the charge, nor does it decrease the speed of the charge, that force, because it never acts in the same direction or in the opposite direction. It always acts perpendicular. When it acts perpendicular, it tends to change only the direction. Okay. So that is the beauty of the magnetic field. Magnetic field actually does not do any work on the charge. So in the next class, let us look at what is the work done by the magnetic field. Like work done by the electric field we have done in the last few chapters. So work done by the magnetic field means how much it increases its energy. So that is what we are going to find out, and is it going to be increasing at all? Okay, we are going to find out in the next session. Thank you.